Hi and welcome to Unit 1, Topic 2, Video 11. And in this video we're going to start looking at some examples of forces and some of the associated assumptions. Now we're going to go a little bit beyond what you need to be able to do, and I'll explain as we go, but it's still important that you can take things a bit further. It's always a nice thing to be able to do. So first we have this shape here. That's an inclined plane. So it's just like a ramp or something like that. We've got an angle theta here acting on that plane. That's an important angle to denote. Now I've already got here a couple of things. We'll start at that pink point, and we've got W, which is equal to mg, mass times gravity. That's our weight. We usually call it W. And then we also have, and I'll do this one in green, because pink and green go really well together, our normal reactive force, which is perpendicular to the plane. Now the other forces that might be acting on this object, at the moment there's no pushing or pulling force, so there's no one there doing anything to the object, but we might also have a frictional force. Now we're going to be careful about assuming where the frictional force is, but I need you to think about this openly for a moment. Okay, the frictional force will happen parallel to the surface. That's the first thing. The second thing is it could happen in either way, but the frictional force will always oppose the motion. So if somebody's pulling on a box, the frictional force will be a force in the opposite direction to the pulling force. It opposes motion. The frictional force will always be in the opposite direction to the pulling force because it opposes motion. So it's important to recognise that you know where the frictional force is. The frictional force can't be going the same way as motion, otherwise it's creating gain in velocity and displacement. And the frictional force is not actually based on energy, or it's not an added energy to the system, it's just an opposing force that slows the system down. So it's always bringing it back towards zero. In this case, the motion, because of the weight is pulling it down the slope, so the frictional force will pull it up the slope. So I've already done my normal and my weight here, and we also have a frictional force pulling it this way, and this is our force diagram. And that's most of our information there. Now we could also have a pushing or pulling force. And then on top of that, in pink, the weight can be resolved into its component form, and instead of doing the old IJ like this, what we're going to do is do I and J based on the slope. Now, I'll just do this little proof for you because it will be important. Here's my slope. Now this weight is going down, and I've got a horizontal line I've invented there. That's a right angle. And this is theta. That is our ramp angle, which means that this angle here is 90 minus theta. And then we are breaking this into its components. One that is parallel to the plane, and one that is perpendicular to the plane. So that means this is the right angle as well, and therefore that angle is theta. So we can break our weight, which is equal to mg, into components, and it's going to be a bit small, but I'm going to zoom in here. That means that this bit here is a cos rule. Cos theta is equal to, in this case, adjacent over hypotenuse, and therefore adjacent is equal to w cos theta, or mg cos theta. You'll see this a lot, and it's a step that you can skip in some questions. For the same reason, this is mg sine theta, or w sine theta. Now, mg most of the time, sometimes you'll just be told that w is 100, and then you've got to skip that mg. So you've got to be able to work around whatever problem you get. Okay, so that's our inclined plane, and there's our cos and sine information. Now, we could have an inclined plane with a weight on a pulley, and we've been told in the last year that the pulleys won't come up in your external exam. So we won't have to deal with pulleys. But again, it's a nice little extension. So this just has a tensional force. There's no addition to it except it's got that tensional force. And if we're talking about this pink star here, so I'm not too worried about the motion there, we're talking about that pink star, it means that we have these forces acting on it. So we have our weight pulling it down, which can be resolved, and our normal reactive force. Now the weight is pulling it down the slope, which means that potentially we've got a frictional force in this direction, but we've also got this tensional force. And the tensional force is equal to m2g, where this object has mass m2, not mg, so M2. So whatever that is, this is going down directly, so it's got weight mg, in this case m2g, and that is pulling the rope this way, which means that the rope is pulling the block that way with a force of m2g. That's our tensional force. Now in this case, and we've got to be careful here to not assume too much about the frictional force, because the tensional force is pulling up the slope. So if this is a heavy mass here, and this is a light mass, well, maybe the tensional force is actually doing more than the weight here, and that would mean that the frictional force is going to oppose the motion up the slope. So there might be enough mass here that the block is being pulled up the slope, and then friction will oppose the motion and head down the slope. So friction could go in both directions in this case. And then we've got this guy here with two pulleys, and then we've basically got a tensional force this way, and we've got weight there. So we're going to have overall W equals mg, and we can go back, we're not on the inclined plane anymore, so we can go back to the old IJ horizontal vertical, which is nice. But we will need to know this angle here, and we will need to know this angle here, or something so that we can work those angles out. But this is our tensional force, tension, well, let's call that 2 with the angle, and tension 1, and they're pulling away. And again, often you'll get a system like this that can be set up so that this block is not going anywhere. And if you get that, or you get that system in equilibrium, then we get an overall vertical component J and horizontal component I that are equal. They're equal to 0. Okay, so there's some of our force diagrams that we could draw. It's important to note here as well, particularly as we move forward, that you might have to deal with some assumptions as well. So some assumptions include no friction in the system, because we're not using friction in this case anyway, so we've got a smooth surface, no friction. A frictionless pulley if we are dealing with pulleys. A weightless string, because a weighted string, or any weight in the string, is going to add weight to the system. But it's, like usually the string is far outweighed by the mass anyway, so there's an assumption there. Surface is smooth, nothing blocking. The block object mass is measured from a point. That's what we're doing essentially, so that's important. And air resistance is negligible. There's a few things to consider moving forward. So you might get a question where you do a lot of work and then you're asked to evaluate the reasonableness of your decision. And here's some things you could talk about. But also you want to make sure that you go back and talk about the maths as well. Okay, so that covers us for video 11 and some systems that you'll see and how we draw the force diagrams. We're going to move now in the next video into some more examples with actual numbers. All the best.